we would love if you wouldn't mind turning on your camera so we can get a group photo. All right, anyone else who wants to join our group photo, please go ahead and just turn on your camera. I know it's early. It's okay. That one. Okay, say cheese. Okay. Thank you. All right. So to get started today, I'd like to welcome you all to the Solar Decathlon Semifinal Competition Event 2023 Design Challenge Division presentations in the Attached Housing Division. Each and every one of our teams has worked hard up until this point on their design projects and will present an 8-minute presentation to industry experts, Alex and Steve here. Based on the presentation today, only 10 finalists will advance to compete in the final competition event in April. In addition to division presentations, we have a few special events planned. We will conclude this weekend with important announcements, including the announcement of our 2023 Design Challenge finalists. Before we begin, we have a few housekeeping items. Okay. Stand by. I'm experiencing technical difficulties, so please stand by for a second. Okay, that has been resolved. So before we begin, we ask you to please keep your cell phones and pagers on silent during the presentations. In all seriousness, please be courteous to each team as they present by staying on mute unless you are presenting. Each presentation will be 8 minutes with 5 minutes of questions and answers. If you should have any technical difficulties, please chat either myself or Jeff in the chat box and we will assist you. I would now like to introduce our esteemed panel of industry expert jurors today, and we will hear about their bios. Okay. So, our first juror is Alex Gamble. Alex Gamble has specialized experience in sustainable design and is responsible for conducting sustainable design charrettes, evaluating sustainable design criteria, methodologies, strategies, and technologies, and making determinations regarding the best approach and solution for construction projects both in the healthcare and residential environments. Alex and his wife Sabrina are the proud parents of Ellie, Elijah, Israel, and twins Ezra and Isaiah. Alex enjoys spending time with his family, traveling, photography, and enjoying churrasco, or Brazilian-style barbecue, which was the traditional staple food of the gauchos, or cowboys of southern Brazil for centuries. Steve Urich is the Chief Programs Officer at the National Fenestration Rating Council, which provides certified thermal performance ratings on fenestration in residential and commercial buildings. NFRC ratings and procedures are the basis for fenestration energy performance, and through NFRC's Efficient Windows collaborative website as a driving factor in the selection of energy-efficient windows by consumers. As the CPO, Steve leads the team that develops and updates the certification programs to meet strategic priorities. Prior to joining the NFRC, Steve spent 10 years at the Building Products Test Lab and another 10 years at an independent building products certification agency. Steve has a bachelor's degree in mechanical engineering from Penn State University and is a licensed engineer in 3 states. So now I'd like to go ahead and begin with today's presentations. So first up today, we have PARS University of Architecture and Art. So we'll stop sharing our screens. If you guys are already on, we invite you to go ahead and load your presentation.
And as a note,
please, I'm sorry.
Go ahead. No, you're good. Go for it. What you got?
No, I was just saying we are ready to present our project, and
Perfect.
Yeah, we can present it whenever you want.
Great. Yeah. So my background screen, just as a heads up, you've got 8 minutes for your portion of the presentation. At 6 minutes in, my background will change to give you a 2-minute warning, and then when the time's up, my background will change to time's up, and then I'll turn it over to Alex and Steve for questions. Yeah, feel free to bring your screen up, and we'll be ready to start when you got it pulled up.
Okay. So can I share my screen, or you'll share the file?
Yeah.
I'm not sure.
No,
okay, great.
You can share it. Yeah, and you guys can drive it.
And while you're loading it, I just want to give a special thanks to Jeff here for all of his hard work at making this semifinal possible. He's been incredible at keeping everything on track and on time, and just, we should give him a big thanks. Jeff is with the Department of Energy, and I, by the way, am with the National Renewable Energy Laboratory, and it's such a pleasure to be here seeing all of your presentations.
Great. So can you see my screen? Is okay?
Yep.
Okay,
yep.
Great. So hello everyone, my name is Tamris, and I'm really happy to be here and present our project to you. Our project is Ramped House, and first of all, I want to provide some information about the location and the site of the project after introducing the team. The site of the project is in Sistan and Balochistan province in Iran, which I want to share something about that with you. This province is the most economically depressed part of the Iran, and detached house within the framework of the governmental social housing called Maskan Mehr is being designed and constructed in there. It is important to know the gas grid and electrical grid are limited, and regarding this special situation in this province in Iran, there is some kind of instability in these energy resources. This province is in Ashray Zone 2, EWH. Our passive solar solutions for this project was the first of all was thermal mass, in particular the ramdares, and the second one was using flow house. The advantage of Ramped House, which I'm going to present for you, is the embodied carbon of this solution, which is very low and gives us the opportunity to engage the local workers in construction phase of the project. And also it is worth mentioning that this solution is very cheap in expenses, and not only is the passive system of our project, but this will act also as the structural system. I want to show you some of the architectural diagrams, which are kind of important to know about our design. And you can see we have two different units, two different types of units, which we designed. And there are some kind of different aspects in architecture and the structure with these two different units. Which we provided. You can see some of the sections and plans of the designed buildings. Yes, you can see some of the renders. Okay, and I want to provide some kind of information about the architectural aspects also. Sorry. I'm sorry, can you see the plans and sections? Okay, great. Well, actually, it's important to mention that we designed, as I previously mentioned, two different types of units, which one of them is kind of 1,400 square feet, and also the second one is 2,100 square feet. We also designed some semi-private spaces between units with the R values, which I'm going to mention. The R values for wall is 32, for roofs is 40, the foundation 40, and also for windows is 4. And yeah. Regarding the engineering part of the project, as I mentioned before, the energy instability is a real trouble for residents of this province. And in this case, the city of Zahedan, and people are using diesel generations and some approaches like that to provide their energy. So after analysis and calculations, we found that we can provide the needed energy just by using photovoltaic cells on the roofs, and the main heating and cooling systems or air source heat pumps, which is kind of reversible. And you can see some details of the wall sections we designed for this particular state in Iran. And the other important fact is about the marketing of the project. Our design buildings will cost 10 to 15 US dollars per square feet. That has a really important difference with the status quo of the similar projects cost, which is about 65 US dollars per square feet now. So although the PV cells and HVAC systems are much than 30% of the total cost, the final result is absolutely meaningful benefits for constructors and people who are going to be residents in this new design. About the durability and resilience, we use the low carbon envelopes, sustainable and local materials, which can provide for us a really sustainable approach. And also there's a potential for maintenance for the construction details and systems we propose for the whole project. Regarding embodied environment, we tried to reduce as much as we could, and the final result is 0.25 tons of carbon dioxide per square feet, which was kind of, as I previously mentioned, meaningful result for us. And regarding the integrated performance of the whole design, I want to mention the regenerative design which we used, and we wanted to consider the system as a whole, and the cost was one of the important targets for us. But about the regenerative design, I think it's the time to kind of elaborate on. We tried to preserve the environment of the system, Balochistan province, and in a bigger perspective, the whole environment of the world with solutions like renders, environmentally friendly materials, energy and transportation management. Although the regenerative design and circular economy is the trend, and we know that, but we're considering the donut economy model because Iran is a developing country and there are so many troubles in social housing foundations, and it's not so easy to just dedicate every other aspect of the design to ecological contributions. Instead of that, we had to make a trade-off between these objectives, like a multi-objective optimization design space or model, if you are kind of familiar with it. Regarding the occupant experience, I want to mention the two important points. We design an architecture to provide the visual and thermal comfortance, and also acoustical comfortance requirements will be met by designing the private and semi-private spaces like that, the yards in the outdoor spaces of project. And about the comfort and environmental quality, we try to design an architecture that meet the needs of the people to have a quality life with the approach of reducing the costs. And about the energy performance, which is really important for us, our design led us to zero heating load with wall details and floor house. So the most important energy consumption will be using cooling, which is kind of natural. Cooling demand is a little bit high in the North London units, and it is the first consequence of the situation of zero heating load. We achieved to reduce the energy consumption from baseline 164 kBTU per square feet to 20.17. And the baseline has been provided by the Department of Energy in Iran. And it is also important to mention that in Iran, we are in a ECNZ category, and with the PV cells, which we propose for this project, we will have zero net energy consumption. So we will have an extra generated. I'm sorry. Yeah.
Sorry, we're at time, but
Just
thank you
one
so much.
sentence.
One sentence.
Yeah, one sentence. With this solution, we will have extra generated energy, which provide the opportunity of dedicating that to the city of Zaida. Thank you.
Thank you. Now we will hand it over to the jurors for 5 minutes of Q&A.
Okay, and also I want to mention that there are some my teammates in here, and Shaweb, Iman, and Zahra. Feel free if you wanted to answer questions if you want. Yeah, please.
I was going to let you go first, Alex.
All right, no problem. I appreciate it. Yeah, great job. A lot of information, a lot of data here. Great job. The rammed earth, that's very impressive. Could you expand on, I guess I didn't see anything in terms of the project summary. Can you walk us through, like, how does the design address the excessive winds or the amount of winds that the project location receives?
Well, actually, we have 120 days of winds in the Zahedan province. And we try to somehow cover these 120 days of winds with our design in location and rotating the whole geometry of the design based on these winds. And yeah, it's kind of a special district in Iran. And yeah, we try to cover the 120 days of winds with
a
rotation of design.
Actually, the orientation of our row houses are north-south in order to use the northern wind, especially if you see our first slide, the wind draws is directly from north. So we try to make orientation to southeast and use the best possible solution for cross ventilation, especially because we have a high cooling demand, and that's because we offset the heating demand by the ramders and thermal harvesting, but we use also cross ventilation with using our winds as a solution for ventilation. If any, I don't know if I missed some points or you would want to go further, I'm free to answer.
Okay, no, appreciate it. No, that was it. And I got one more question, then I'll turn it over to Steve. Going back to that rammed earth detail, it's kind of like a zoomed up of that wall. Could you just walk me through what's the PVC part? Is that another wall coming on top, interlocking with the rammed earth wall, or?
Tammuz, could you share the detail of the ramders?
Sure.
I think it's in engineering about slide 20 or something like this. Far above.
I believe it's 20.
Okay, here. Would you mind zooming in? One,
sure.
Not this one. Here. Yes. Slide 21. We try to insulate the whole building. Because of that, we have two separate ramders. First, the inner layer, then we have the insulation that's cover whole building. After that, we have the second ramders, which these two ramders work like a heating buffer that somehow regulate the temperature of outside and inside. And also because of different layer of soil, we have some aesthetical architecture, representation of ramders. If I miss any point, just let me know.
No, that was great. Thank you.
Thank you so much.
Excuse me. Yeah, that was good job. I really like that rammed earth wall design that you have there. I do have a question about the atrium area, I think, like your courtyard area. Is that fully enclosed in glass?
It's fully enclosed in glass, but the glass is operable. And we use somehow the buoyancy effect also to assist the ventilation from the yard.
Okay, okay. That was actually my question because I was afraid of overheating.
No,
in there
it's
again.
not the
So-
heating load trap there. We think of that.
okay.
Also, especially on top, it's going to be operable because the access to the roof is from the yard, and it's
Okay.
somehow not, instead of ventilation and beside the ventilation, it should be operable because it's the access to the roof.
Okay. Okay.
Right, that
Very
brings us
good.
to time. Thank you so much, everyone.
Thank
We
you so
will
much
now
for
Thank you.
assisting us.
Thank
you.
you, guys. Thanks.
We'll now give the jurors a few minutes to deliberate. If Texas A&M University and Hanoi University of Civil Engineering would like to go ahead and pull up their slides, we will begin at 10:25 Eastern Time.
Hello, can you see my slide?
Yes, we can see your
Yes.
slides.
Thank you so much.
All right, would you like to go ahead and get started?
Yes, of course. Antonio, Kaida, are you ready?
Yes.
Yes, thanks.
Yeah, go ahead.
Okay, well, good morning, everyone. My name is Antonio, and my teammates Gaira, Luming, and I will be introducing this project on behalf of the Texas A&M University and Hanoi University of Civil Engineering Solar Decathlon team. So our project for the attached housing division is called Kuo Key Houses. We have a multidisciplinary team of architecture and construction science students from both universities and faculty advisors from both. These are our industry and design partners. I would like to highlight that we collaborated with the Ministry of Construction of Vietnam and 1+1 greater than 2, which is a Vietnamese design and construction firm. So this project is located in Kuo Key Village within the Cao Bang region of northern Vietnam. It consists of 3 attached houses. Our objective with this project is to propose a sensible intervention that addresses existing problems related to access to energy, living conditions, lifestyle, and the economy. Kuo Key Village is inhabited by members of the Thai ethnic group, and 14 multi-generational families make up its whole population. It's located in a mountainous region, 951 feet above sea level. They have an agricultural and livestock-based economy, although due to the proximity to the Bang Yak waterfalls, there's a growing tourist homestay market in the village. So the team had the opportunity to visit the village and survey a neighboring house. Indoor illuminance, temperature, and air velocity were measured to assess the indoor environmental quality. We found that the locals generally live in poor ventilated spaces, dark interiors, and cold interior environments. This analysis of their existing conditions helped us to define our design goals. Our project is in a region characterized as having a temperate climate with a dry winter season and a hot summer season in latitude 22. A more detailed analysis of the climate utilizing a local weather data file confirmed the temperate nature of the climate and its predominant cold and hot seasons. Furthermore, a natural ventilation potential analysis was conducted. In this location, there are prevailing winds from the south during the hot season, which is when natural ventilation will be more desirable. Using a modified comfort range of the Vietnamese people, we concluded that passive design strategies such as internal heat gains and natural ventilation could be used to provide thermal comfort during 80% of the year and only require supplementary heating and cooling during 20% of the year, thus ensuring the lowest possible reliance on energy consumption. So our design addresses 5 goals: quality of life by improving indoor environmental quality; sensibility, the project respects and embodies local customs and architectural features; passive design strategies such as natural ventilation, daylighting, and shading to ensure comfort and low energy consumption; constructability was studied to prioritize the use of locally sourced materials and low-skilled construction techniques; and finally, the resilience towards flooding and landslide hazards. The site plan shows the location of our project within the village. We designed two two-bedroom units, A and C, and one one-bedroom unit, B. The attached houses are joined by an outdoor veranda that is oriented towards the southeast, in part to respond to local building customs, but also to provide access to the prevailing summer winds and views towards the landscape. The buildings were separated to facilitate natural ventilation and access to daylighting, and harvest drying areas are provided in the gaps between the buildings.
So we integrated multiple technologies that include retaining walls, vegetation, low-in windows, solar panels, passive technology, low embodied energy material, and local architectural features. For the natural ventilation, here the first diagram shows our design reduces stale air in the kitchen area. The second one shows our air change design exceeds the ASHRAE standard. Sorry, the last one shows after adopting the care story, we will have very good natural ventilation in the living area. For the solar studies, we maximize the solar access for photovoltaics, daylighting, and optimize the shading design. The right diagram shows we have very good daylight performance, which shows every space exceeds 300 luxes at least during the daytime and control the glare effect very well in all directions. For the envelope, we were using local materials with good performance and easy access in that region. We selected a continuous insulation system with low carbon and low scale construction techniques that local people can build their building easily.
The selection of energy-efficient building materials was based on reduction of embodied carbon by using local materials to reduce transportation-related emissions. At the same time, the use of local biogenic materials can store carbon to offset operational carbon emissions. To address the flooding and landslide hazards, we adopted the local bamboo for protecting buildings, which can stabilize the soil on the back of our site. At the same time, we elevated the building to avoid floods. We also designed a rainwater harvesting system to collect and store water for irrigation and domestic use. We used EUI and HERS to evaluate the energy performance. Before solar panels, we achieved 4.3 to 4.5 EUI for each unit, and with solar panels, we got 0. In HERS, we got 34 to 36 without solar panels and 4 to 8 with solar panels. Our design exceeds AIA 2030 challenge requirements and is more efficient than RESNet reference home. We selected a 22% efficiency PV panels. The kilowattage and PV area was sized based on the daily energy consumption. Regarding the mechanical system, the key idea here is that we were using smart air conditioning system that is based on occupants' movement and to achieve both comfort and energy efficiency.
The plan for our final submission is organized in 5 phases. We will kick off the final submission after this presentation. After that, we plan to communicate with our design and the industry partner to improve and finalize our design. For the last 3 weeks, we will focus on comparing the narratives and schedule of NREL traveling. So to sum up, our project improves existing living conditions for the occupants, reduces energy consumption through the use of passive strategies, incorporate local architectural features and lifestyles, use locally sourced material and low-skill construction technique, respond to nature hazard, and propose an adaptable and affordable housing prototype for future development in that region. Thank you.
Great job, guys. Yeah, really well done. And with that, we'll turn it over to Alex and Steve.
Good morning, guys. That was an excellent job. I do have a question for you. If you go back to your overhead picture of the site, I think it was like the second or third slide that you had there. Currently, it looks like the site is wooded. And if so, are you're planning on obviously clearing it for the houses then?
Yes, that is correct.
Okay. Are you planning on using that wood in the project itself as part of the construction materials?
So actually here we have a hybrid structure system here. On the ground floor, we were using the stone structure there because this is available in that region market, and the people there are familiar with those stone structure on the ground floor. And also because we have a flooding issues, we elevate our building to the second floor with the main living area. So the second floor becomes like the main wooden framing structure there. And because the material is very light and eco-friendly with low embodied carbon, and all the most good things is have very good thermal performance compared to other material like concrete or stone.
Okay. Okay. I think you answered that then. All right. I think that's all that I really had for you. There was a lot of detail in there and answered a lot of the questions that I've been asking of other teams. So thank you. Good job.
Thank you.
Thank you.
Yeah, great job, ladies and gentlemen. Very detailed. With respect to the waste utility, how is that being addressed in this project?
You mean the utility fee?
No, the sewer. I saw that there the toilets and all that. Is it going to a city or local municipality treatment, or is it treated on site?
Yes, our project is located in a rural area, so we have very I would say not very good civic sewer system. So our idea is to keep the contour of the existing condition. Like you can see on the back of the site, we have a mountain, and we're trying to do not change too much elevation our site. Then we still can navigate the rainwater to the lowest point to the river in front of our site. This is a product consideration, but still, if the local have the good civic drainage system, we will connect to as well.
Yeah, and Alex, we're also considering using septic tank, basically.
Okay, yeah, I didn't see anything that reflected that. I understand the storm water, you know, but again, black water, right? How's that?
Yeah.
You know, that's got to be important here. Second question. I know it said it was an agricultural and livestock economy. Other than the harvest dry area, how does this design take into account the people's use and reliance on livestock? How does the design address, and I don't know what kind of livestock they're raising, maintaining, but how does the design address that? And then going back to that, where there's animals, then there's waste. How does that happen?
So part of our design, we mentioned we kind of like embodied local architectural features. So actually here, all the houses have like they're elevated, and their first floor functions as a storage space, and they keep kind of like livestock in the first level. So that's also part of elevating the houses. So that first floor is actually seems to be very important to them for that use.
Okay. Yeah, that makes sense. Because in I guess in one of the sections I saw it looked like there was bicycle storage or things like that happening.
Yes, on the ground floor, we consider for the avoid the flooding issue, so we'll elevate the main living space to the second floor. But at the same time, the ground floor will become like a multifunctional for the future use that can decided by the future occupant. So can be the store for the agricultural products. I think it can be a parking space.
Okay, and then one last question. Those little channels
Actually,
there, are those the channels, the stormwater channels? Oh, Julie, are we out of time?
we're out of time. I'm
Okay.
sorry.
All right. Thank you.
Great questions, though, and great answers.
Thank you so much.
Thank you so much to Texas A&M University and Hanoi University of Civil Engineering. We will give our jurors a few minutes to take any notes they might have. And if University of Tennessee at Chattanooga would like to go ahead and pull up their slides, they may do so, and we will get started at 10:40 a.m. Eastern Time.
Well, thank you and good luck to the other teams.
Thank you.
Thank you.
All right, if you are ready, you can go ahead and kick us off. This is University of Tennessee at Chattanooga.
All right, can you guys hear me?
Yes.
Perfect. Perfect. All right, good morning, everyone. Thank you for joining us as we present our net zero solution for Nugaplex. Through our partnership with Chattanooga Neighborhood Enterprise, also known as CNE, we set out to redesign their current attached housing facility. CNE is an affordable housing nonprofit organization in Chattanooga, Tennessee, and they focus on prices that are 30% lower than the market price of the Chattanooga area. Our goals for this project were to achieve net zero energy, elevated occupant experience, scalability, and affordability to align with CNE's mission. And welcome to the Solar Mox team.
CNE's missing middle housing design was conceived as affordable housing. The two-story building contains 6 apartment units with 3 units per floor. Each floor consists of a mix of 2-bedroom and 1-bedroom units with a total of 1,800 gross square feet per floor. The Nugaplex is our proposed net zero solution to CNE's current attached housing design. Nugaplex is a 6-unit attached housing facility centered around the overall improvement of design and materiality. The new design retains the best features of the existing design while improving the building and achieving lower energy consumption. Nugaplex is designed to be approachable and familiar to the local community, which is largely centered around the idea of a front porch community while also fitting into the future of the city. The building from a glance looks like a single-family home. Each unit features their own porch to tie in the idea of a front porch community, while a modern double-shed roof combines with a traditional gable to blend in with the housing styles in the area. The area surrounding our site only contains 2 original houses. The rest of the area is being renovated rather quickly. And then these are the topics that we will be covering today.
Considering our target market is families with children, 2-bedroom units are a key part of the space planning and design. Nugaplex has a 2-bedroom unit option and a 1-bedroom studio unit to serve the majority of CNE clients, which fall in the range of 18 to 25-year-olds.
Considering our target market is families with children, 2-bed units are a key part of the space planning and design. Nugaplex is a 2-bedroom unit option and a 1-bedroom/studio unit to serve the majority of CNE clients, which fall in the range of 18 to 25 years old.
Chattanooga is located in the International Energy Conservation Zone 4A. We have a warm, humid climate with our lowest temperatures dropping 0 to 5 degrees Fahrenheit. Our average hottest temperature of the year is around 89 degrees. Chattanooga has a high humidity levels where our cloud coverage varies largely based on season. In terms of solar energy, our brightest months are from April to September, with our darker period lasting from November to February. Situated in the southeast side of Chattanooga, adjacent to I-24, the site lies facing northeast. The Nugaplex will have the most solar exposure on the southern facade throughout the day.
Chattanooga has been a rapidly growing city in recent years, which has led to the housing market rapidly increasing alongside it. Our job market lies largely in the technology, healthcare, and education industries. Our site is located near many amenities, including schools, hospitals, restaurants, and more, which maximizes access to the public transportation and the walkability of the site.
Breaking down C&E's current design, we can analyze multiple design issues that can be altered to improve the building's energy efficiency. This entails poor placement of water walls, limited outdoor access for occupants, basic architectural aesthetic, excessive use of windows, inefficient systems, and poor insulation. The architectural response for the new building retains the overall form by sharing a single roof with a breezeway and stairway through the center. The roof design has been changed from a hip roof to a mixture of attached sheds and gable, which provides more visual interest at the request of C&E and one that melds traditional lines with modern design. The building makes use of the natural site conditions, which affect window placement, fenestration, and overall aesthetics of the building.
Sydney's design was rather basic from an engineering standpoint. Though the construction was simple, it failed to adequately account for air leakage. It also sacrificed a lot of space to an unused attic and had complicated HVAC and plumbing networks. To reduce air leakage and improve R values, we utilized expansion foam insulation. We simplified the plumbing and HVAC systems by changing to a ductless mini split and running most of the refrigerant lines and all of the plumbing through a central wall. To take advantage of the attic space, we added an extra room on one side and hid the water and heating ventilation equipment in an easily accessible mechanical room on the other. Having this equipment separated from the resident means that it is quieter and can be accessed for maintenance without having to enter the tenant's home. Running the ERV through the attic also allowed us to ventilate the attic and cut out expensive ducting runs.
Overall, in Chattanooga, a total of 43% of the population is cost burdened, with a median rent of $850 for renters and an annual household income below $40,000. The proposed design for the Nugaplex can offer alternative housing options for those who pay more than 30% of their monthly income on housing. Nugaplex improves the construction industry through working with local suppliers, enhancing reputation, and encouraging community engagement. The demand for this improvement within the construction industry comes from maximizing affordability, designing for efficiency, and prioritizing renewable energy. Nugaplex has the same dollar per square footage for construction costs as the C&E design. The only major difference being that Nugaplex has a larger built area. This is counteracted through overall utility savings, which equals $1,018 annually.
A large part of our plan focused on ensuring a long lifespan and low maintenance requirements. For the structure, this meant using materials that are strong, environmentally resistant, and eco-friendly, such as pulverized fuel ash concrete for the foundation and reclaimed wood for the framing. For the appliances, it meant ensuing ease of maintenance and a minimum 20-year lifespan where possible.
Our plan is to use a zero carbon structural design method by reducing the environmental impact of upfront carbon emissions from materials. Building materials are proportionally categorized as being recycled, reused, and diverted from landfill during construction and at the end of the building's life cycle wherever possible.
All of the electrical and HVAC systems were chosen to complement and benefit each other. To reduce electricity demand, we incorporated energy recuperation strategies such as an ERV and a waste heat concentrator, which captures heat from the AC system to preheat water for the tankless water heaters. Additionally, we chose efficient appliances and utilized passive cooling strategies wherever possible, which improved overall air quality and reduced the number of air changes per hour required to maintain a healthy environment.
The original plan's window placement resulted in a space that gained a lot of unwanted heat through the east and west sides of the building, increasing the amount of energy that would be spent to lower the interior thermal environment. These windows also resulted in hot spots that brought about harsh glares, and the overall interior environment had poorly diffused daylighting. Nugaplex's proposed design takes advantage of the north and south facing windows to create a symbiotic relationship between the thermal environment and the proposed heating and cooling systems. This integrated approach has resulted in softer, well-diffused daylight within the space and the energy savings in the long run. The Nugaplex is designed with user experience in mind, focusing on integrating design solutions to enhance occupant experience through color psychology, thermal comfort, circadian rhythm regularity, and community has achieved a high level of functionality. With the addition of specifying sustainable products, site-specific design, the building envelope positively affects the health and well-being of both the interior and exterior environment.
Thanks to the various efficiency solutions used in this project, we were able to reduce the energy bill by 15%, which significantly adds to C&E's ability to provide affordable housing. This energy reduction meant that we were able to cover the remaining energy needs with a single large solar array, which could be easily added to the large southeast facing roof either during construction or as funds allow, without sacrificing any of the original design characteristics.
Thank you so much, Darren. Oh, and you are at your last slide, so thank you. We will pass it on for questions and answers.
Am I going, Steve?
Go ahead. I lost
All right.
track again.
Yeah. Appreciate it. Job well done, ladies and gentlemen. Especially evaluating, understanding C&E's baseline design, right, in their targeted market. Kudos for that analysis. Question, how did C&E react to your evaluating their design, their inefficient design?
I can answer this one. In our meeting with them, they were actually pretty happy to hear our feedback because they obviously, on a lower budget, don't get a lot of opportunities to really hash out these designs with their architects and their engineers. So when we were able to show them, that with a little bit of redesign, they were able to get a lot more efficiency. They were very happy to hear that.
Okay, good. And with that being said, what was the outcome? What did they take away from that other than the gain efficiencies? But was there anything else that they took away from that little study? Because as we all know, the things we already know is of no value. It's the things that we don't know that's of value, right?
So part of our project was to try to make this design scalable. So in the future, if C&E wants to kind of take these design principles and use them for further projects, we've tried to make it so that with minimal changes, it can adapt to the area. So very much, I think this has the potential to change their entire design philosophy going forward, not just this one unit.
Okay, appreciate it. Thank you. Steve?
All right. Thanks, guys. Thanks, Alex. So I was a little concerned. I was looking at the size of the units. You have a 2-bedroom unit there at 400 square feet. Did I read that right? Yeah. So that bottom unit says 2-bed, 408 square feet.
Yes.
Or something like that. Okay.
Yes.
Okay. And C&E didn't say anything about losing that size, because I think if you go up one, their 2-bedroom unit was like 700 square feet.
For C&E, whenever we talk to them about how they do rent and stuff, because they focus on affordability, they do their rent more centered around not square footage, but how many bedrooms the space have. They have a base rate for a 2-bedroom regardless of the size of it. Did that answer your question?
Sort of, I guess. I don't know. I'm a little worried, about. I have kids. I love my kids dearly. One of us is not coming out of a 400 square foot apartment if we're living together for many years. So, yeah, that's just my take on that. So, the other question that I had for you, it looked like that loft area, I think, and I forget what slide that was on. There was somebody standing in the loft area there. That is accessible by tenants. And is that for mechanical storage and use?
One side was for the tenants, the taller side, and then on the other, that's where we had the mechanical room, and that's a little bit lower ceiling.
Okay. But it is accessible then, so you can get in for maintenance and things like that?
Yes,
too?
that's where we place the ERVs and the water heaters so that you can get in there for maintenance and change filters without having to disturb the tenants.
Okay. And then just that top floor, I guess, has access to that other space?
Yes.
Yes. Okay. I think that was all that I had. So thank you. Good job.
Before we go, I'm going
Appreciate
to
it.
quickly apologize for talking over my teammate. I could not hear her. So sorry if that caused confusion.
That's all right.
All right, well, thank you so much to the University of Tennessee at Chattanooga. We appreciate your coming out and presenting today. And with that, we'll give the jurors a few moments to write down any notes they might have. And if Vermont Technical College would like to go ahead and pull up their presentation, they may do so, and we will plan on starting at 10:55 a.m. Eastern Time. I think you might have your captioning on, just so you're aware. Oh. All right, well, if you would like to go ahead and get started, this is Vermont Technical College.
Well, I'm just trying to figure out the whole Zoom thing. Give me a second.
Take your time.
Okay. There we go. I'm just waiting for my teammate who's having a minute to get in. He's having an issue.
Okay. Let me check if he's in the waiting room.
I could get us started until they come in, I guess. If that.
It's okay. We can still wait a minute or so.
Okay,
For your
yeah.
ballot. Yeah, no worries. Just gives our jurors more time for notes, you know?
Extensive notes. Because it's not connecting for him, so I don't.
Could he call in, perhaps?
I think we'll just get started until he maybe figures it out. I think Jeremy's on the call though, so. Or not. There we go. I hear him now. Okay, I'll just get it started, I guess. So we're Vermont Technical College. And so this is our team for the whole team. Right now, presenting it's just myself, Alyssa, and Jeremy, and Alex may or may not be joining us if he can get it to work. But the rest of our team includes our Professor Riley, who was our advisor, myself, Simone, who also did architectural with me. We got Ryder, who helped with the electrical and systems. Matthew and Levi both did the HVAC. And then Jeremy and Alex did kind of the rest of the in-between that we'll get into during this presentation. So trying to move my thing so I can see. There we go. So Governor Phil Scott signed a historic housing legislation into the law about how, and our main focus for this thing, the law that he put in was how can zero energy design take full advantage of this bill to maximize affordable home construction, which is what we're going to get into during this presentation. So our project was based in Vermont, and it's in a Randolph Center, which is right down the road from our campus. It's 32 acres, and in the picture on the top, the two black squares are our two buildings that we're going to propose. They're kind of set far off of the road, but the interstate is right down the road, so it makes it for easy access to get anywhere. So during our drafting phase, we had one main goal before we even started, and that was kind of, what do we want it to look like? What does Vermont need? Specifically, what does Randolph need in the area? If you've never been to Randolph, there's not a lot in Randolph. So trying to get people to come to Randolph was one of our goals. But the whole feel of the design was to get a cabin feel, but with some modern finishes. So we have two buildings. Each unit is about a 30 by 30 with a lot of natural light. There's a lot of windows. And they can hold, each building can hold about 38 people. And so the whole building includes 4 2-bedroom units, or both buildings include 4 2-bedroom units, 4 3-bedroom units, and 2 4-bedroom units. So the 2-bedroom units are on the outside. The 3 bedrooms are in the middle wings. And then the big middle center is our 4-bedroom unit. So these are some of our renderings from our Revit model. So the picture, there's a kitchen, which each kitchen is kind of different in each unit. But as you can see, the big windows that we have, a lot of open space. So these are our floor plans. So our main goal when doing the design was we wanted to keep everything up to date. We wanted people to have their own space. So each unit includes a 1-car garage. And then if there is another car or more cars, there is parking. But there is going to be an additional parking lot as well with a canopy over it. So the snow doesn't, so you don't have to clean your car off every day in the winter. So each unit also includes an in-house washer and dryer, so you don't have to go to a laundromat. They have full-size kitchens. They're 2 bedrooms or more. Each one includes a balcony, full-size closets, and up-to-date appliances. So the building is staggered to give a sense of privacy because the 2 outside units have the balcony on the front. The ones in the middle wings are in the back, and then the balcony in the center is in the front. So the staggering makes it so that you have more privacy, which was also one of our options that we wanted people to have since you're living in such kind of close quarters. So now Jeremy's going to talk about envelope and detailing.
The materials that we chose for the envelope are all sourced within 200 miles of the project site to minimize carbon footprint. And the design was focused on ease of construction and to reduce the construction costs primarily, and also the quality of the living experience for the inhabitants. As you can see, the big pink in the center is 6-inch timber frames that are infilled by SIP panels, which provide the vapor barrier to the exterior of the structure and allows the interior to dry to the interior and the exterior to dry to the exterior. Then moving to the exterior, it's 2 inches of rock wool and then a 1 3/4 inch air gap and locally sourced plywood siding. And to the interior, there's 2 inches of hempcrete and a 3/4 inch plaster finish. And that allows for the best moisture management that could be easily achieved. On the roof, we've got 2 layers of SIP panels to provide an R60 roof. It's an R40 wall and an R20 slab and footing. And the entire construction time is intended to be rather quick. compared to a lot of things. And we've got the square footage cost was around $300, if that was correct, Melissa. And the monthly expenses to inhabitants would be under $600, which is well below market rates. And I believe Alex will be joining us for the systems now.
Yeah, so we'll start out with the HVAC system. We chose to go with a geothermal heat pump due to our area and our climate and where we're at. We thought that would be the most energy efficient design. Throughout the seasons, we have a lot of temperature change from summer to winter. So a geothermal heat pump gives us the most consistent ground temperature. And we chose to go with 300-foot deep wells. So our HVAC unit we chose is going to be the Train Axiom High Efficiency. It's going to be the ground loop heat pump. And sizes on these range from 2.475 to 3.625 tons, just depending on the occupancy of each unit will depend on the size of unit we choose for each. So plumbing, everything is going to be high efficiency plumbing. Obviously low water usage and consumption. And the way we met our goals for the low water usage and consumption are just low flow fixtures. And we also chose to go with a rainwater harvesting system. And each individual building will have its own rainwater harvesting system.
All right. Thank you, Alex. We are at time, unfortunately. But thank you so much to Vermont Technical College. We'll now open it up for Q&A to the jurors.
Good morning, folks. Thank you for the presentation. We appreciate it. I do have a couple questions. If you can go back to the floor plan for me. It looks like each unit has its own stairway down to the garage.
Yes.
For access to their vehicles. And that's okay with fire code?
Yes, because so each unit, when researching into this, so each unit can have its own fire code as long, or its own stairwell in its building, as long as you meet the fire system regulations. So make sure you have sprinkler systems in the stairwell.
Okay.
Make sure you have the horn strobes, and it had to be a certain area and a certain amount of stairs. But I don't remember it off the top of my head.
Okay, that's fine. It was more just kind of an egress question. Making sure
there's
you could get
giant
out,
windows
and it was fine. So yeah, that's fine. And then the systems, I know we went over that real quick. You were doing one of the ground source heat pumps per building or one per unit?
Yeah, so I believe we sized one per building.
Okay.
And that size is dependent upon the occupancy of each building.
Yeah. Okay. I just wasn't sure.
Yep. Sorry about that.
No, that's okay. That's why we're here, to ask questions. And then, did you guys consider putting the photovoltaics on the covered parking? Is that where it is, or is it on the roof of the buildings?
Yeah, and so on that covered parking, it's going to be filled with the photovoltaics, and
okay.
And anything excess that we couldn't make up is going to be ground mounted.
Okay. And Alex, if you don't mind, one last question. What made you pick that location on your site for the buildings?
So that is a really good question. Because not going there, it would be, I understand the question. There's a mountain range that those face.
Okay.
And the orientation on that east-west axis allows us to maximize solar gains in the winter as well as minimize in the summer.
Okay, I just wasn't sure why maybe you didn't make it closer to the road or something like that. Are there plans to put up more buildings in the future?
So not necessarily on this site, although potentially. This is kind of an interchangeable design that can be replicable to any site that we see fit. But we, like I said, that we in trying to showcase the Vermont scenery, that there's a mountain range there, that it looks out over, and so
Okay.
yeah.
Okay. Thanks.
Yeah, thank you, Steve. Great job, everyone. In terms of the geothermal system, is that a vertical or a horizontal system?
So that's going to be a vertical system.
Okay. And were there any thoughts where to place that? The wells?
Yeah, I believe our location for those is going to be, it'll be actually north of the buildings you see in the image before you, which is out behind the units themselves.
Okay. And second question, were there any considerations from the impacts from being close to that, I guess that's a state highway 66 in terms of noise or pollution?
Yeah, so believe it or not, that road actually doesn't get that much traffic. The only traffic it sees is the small amount of people that go to Vermont Technical College, really. So the noise really wasn't a concern for us. And the separation distance on those units from that state highway is about 500 feet. So we figured that was enough separation, and that's part of the reason we placed the building so deep into that lot.
Right. Okay. And last question, were there any energy or building simulation regarding all the amount of glazing and double volumes spaces you have in the building interior?
Jeremy, did you want to answer that one?
Yeah. We don't have access to the software for building analysis, but we did do hand calculations about the solar gain based on times of year, and designed our passive solar shading to mitigate the incoming solar gain in the summertime. And in the wintertime, the windows are positioned to take advantage of the thermal mass of the hempcrete interior cladding as well.
Okay, good. Thank you.
All right, everyone, we are at time. So thank you so much for the questions. Thank you so much for the presentation, Vermont Technical College. We appreciate it. We're going to go on a 10-minute break. So if everyone could plan to be back here at 11:20 a.m. Eastern Time, that's 9 minutes from now, we would greatly appreciate that.
Thanks, everyone.
Thank you, Julia.
All right, we are back from break. If University of Cincinnati is back, you can go ahead and pull up your slides.
Ben should be putting up our slides right now. We're all here.
Excellent, excellent. Right, when you're ready, you can go ahead and kick us off.
Perfect. So we are doing attached senior housing. And my name is Abigail Gronauer.
I'm Madeline Shackle.
I'm Riley Renner. And we also have Ben Mora on the slides. Our other two teammates couldn't make it today.
So our site is located in Gouda, Netherlands, approximately 45 minutes from Amsterdam, and is occupying the southernmost portion of a net zero corridor. This site is located relatively close to the main roads that run through Gouda and is situated 3 blocks from the River District in a predominantly residential area. Approximately 10 to 15 blocks from our site is Gouda's main historic district and downtown area. One important thing to note is that cycling, walking, and public transit are the most common types of transportation in the Netherlands, with 36% of Dutch people listing biking as their most frequent way of getting around. The climate in Gouda is temperate and can be classified as a 4C climate zone. It has cool, wet winters and mild, relatively dry summers, with highs in the 70s and lows in the 30s, and moderate rainfall throughout the year. Our site specifically experiences prevailing winds from the southwest corner of the site, with an average wind speed of 11 miles per hour. Additionally, our site experiences southern lighting, which is not obscured by the surrounding buildings. The length of the day in Gouda varies widely throughout the year, with an average of 12.27 hours of sunlight a day. This shows the proposed net zero corridor with our attached housing development located at the southernmost portion of the site. Our portion of the site has 3 identical buildings, each with 4 units. The layout and design of our site was largely influenced by the weather patterns and community of Gouda, and it led us to have 3 main goals when creating our design. Our first goal was to create an accessible housing with convertible spaces where residents would be able to age in place. This meant that our site and buildings had to be navigable at all ages. To accomplish this, we ensured that there were no steps throughout our site, so it was easy to navigate and ADA accessible. Each unit also features convertible spaces to aid with aging in place. Second, we wanted to create public and private spaces for our residents and surrounding communities to enjoy. To create these public spaces, we started by creating a walking path that runs through our entire site and leads to places like our vegetable and wind garden and rose garden. Each unit also has private patios and balconies for residents to enjoy. Our third design goal was that we wanted to create a sustainable environment for our residents. To do this, we first looked at ways to reduce maintenance within each unit and around the site. We opted for durable materials that wouldn't wear over time. We also wanted to mitigate variable expenses our residents might have, so we provided 2 energy harvesting systems in the form of solar panels and wind turbines, which in theory should produce energy opposite to each other.
Now for our architectural design. As mentioned earlier, we have 3 buildings on our site, each including 2 3-bedroom units and 2 2-bedroom units. Since we are focusing on aging in place, our floor plans have all essential functions on the first floor, with an additional bedrooms, bathrooms, and balconies on the second floor. The areas in green reflect our green roof, and the areas in gray are where our solar panel will go. In the aging in place experience for one of our 3-bedroom units, it is typical for all of our units. In this scenario, we are looking at a couple who has just retired and recently moved into this unit. The residents are at a more physical capable stage in their lives where they share a bedroom and use 2 bedrooms downstairs as an office or den. Phase 2, they can move the main bedroom downstairs, assuming one resident can no longer use the steps, and they convert the upstairs space into a guest bedroom for family visiting. Finally, in phase 3, each resident has their bedroom on the main floor, assuming neither of them can physically use the stairs anymore. The second floor can remain as a guest bedroom, or the residents can use that space for an at-home caretaker. The caretaker has the space to add a kitchenette. If the residents opt out of having an in-home caretaker, they can have the option to convert the closet into an elevator. Here is a view of a typical furniture layout throughout the main living space of our units.
Overall, our design was heavily influenced by passive design strategies, starting with our 6 wind turbines located on our northwest end of our site. We have 2 wind turbines dedicated to powering each building. And then we also have a green roof. This will add insulation, improve air quality, reduce urban heat island effect, improve biodiversity, and help with our stormwater runoff. Secondly, we have solar panels on our roof and also a shared bike path that has solar panels on it. They face the south to collect the most amount of sun. We really tried to make our envelope airtight so that it would reduce infiltration and increase heat retention. We also have shading elements above each of our windows so that in the summer sun, it is shading and not allowing the heat to get into our building so that we have to cool more, but also allowing the winter sun to enter those windows and passively heat our building. The orientation of our building is south facing for our solar panels and for daylighting strategies. Our open spaces allow for that daylighting to reach all the corners of our units. We have reflective spaces to also aid that, and the open spaces help with a lot of air circulation as well. For our mechanical design, we have a ground source heat pumps located on the northeast corner of our building that serves all of our units. This ground source heat pump pumps refrigerant to each of our heat pumps that are located in the main areas of each unit. And then we also have dedicated outside air systems in the first floor of the bedrooms. We wanted to put it there so that when our CO2 sensors go off, outside air is directly getting to our sleeping occupants, and also helps with exhausting our bathrooms. We have to have that for our airtight envelope as well. And then lastly, our ground source heat pump also has a heat exchanger with our domestic hot water tank to preliminary heat our domestic hot water before it uses electricity to heat our domestic hot water. And then lastly, it brings us to our energy efficient measure breakdowns. We started our energy model with a base case building that is just ASHRAE code minimum, and that is a 73.4 EUI. In effort to reduce those, we looked at our lighting power density, and reducing that brought us to a 57.8 EUI. And then for our second EM, we had an equipment power density reduction, which brought us all the way down to a 32.4 EUI. We looked at other measures, but these two were the most significant for us. This brings us to our production. We have PV on our roof, and that generates about 25.4 EUI of electricity per building. This brings our building over to up to a 7 EUI overall. And then we added our wind. We have 2 turbines dedicated per building to generate electricity. They generate around 6.1 EUI per building, bringing us to a 0.9 EUI overall. Lastly, we have a shared bike PV path, and that generates around 4.5 EUI of electricity per building, and that brings us to an overall EUI of negative 3.5, making us a net positive, meaning that we generate more electricity than we consume. And that is all for our little brief 8-minute presentation on our project. We hope you enjoyed it. Thank you.
Thank you so much, Riley. Now we'll open things up to the jurors for questions.
Am I going, Steve, or would you like to go? Can you hear me?
Yeah, jump in. Go for it.
Okay. Well, I guess I'll go first. Great job. Let me ask, what influenced this project site location?
So our professor actually has family that lives in this area. And there was this large, the town has kind of this large, what they classified as like not very pleasant to look at parking lot. And so our goal with that was to convert it into a more desirable space for the community.
Okay.
I think that it was an effort to get us to try to expand like our traditional engineering, like we're all obviously have ideas of like the code requirements for America. So it was definitely a huge challenge for us to figure out the Netherlands codes, and especially like our design was heavily influenced by typical buildings over there. And it's just really not the same as American. It's a lot smaller and a lot different. So we just kind of wanted to stretch our abilities there.
Right. Okay. So with that being said, if this development were to replace that parking lot, did the project consider, or what happens to that parking lot? There's a need for it, right?
Right. Go ahead, Abby.
Yeah, so there currently the parking lot has storage containers on it, like little, like kind of like the pods that you would rent to put outside of your house. And in the Netherlands, having a personal vehicle isn't very common. And the government does a lot to encourage people to use public transit. And like I mentioned earlier in our presentation, biking and just like walking is a lot more common than driving. In addition, like we are providing some parking throughout our site. So we added 2 main roads that run the entirety of our site through 4 different buildings. Those have parallel parking spots located along the side of those. And then for our residents, we did provide 2 parking spaces for each unit. So they shouldn't be taking any of those parking spaces from anybody that would need them along the street.
Okay. And last question, in terms of the aging in place caretakers, what were the considerations for that population, right? That targeted market
Yeah,
in this
so
whole project?
Yeah, so we originally were having 1 story. Our plan was to do 1-story buildings with all essential functions on the first floor. After doing more research into kind of like retirement homes in the Netherlands and in Europe, they're actually pushing people to get in-home caretakers instead of putting people into retirement facilities, as they found that it makes like people more comfortable as they're aging to stay in their own space instead of moving to a new space towards the end of their life. So that was kind of something that was very different, I feel like, culturally from the United States. So we decided that, you know, we would give each unit that ability to have a private space upstairs for an in-home caretaker instead of, you know, like we want this to be a place that somebody can come and live out the last 20, 30 years of their life after they retire. So we just really wanted to make sure that we were providing them all of those options. And we thought, like, if maybe you don't need an at-home caretaker, it's a great space for, you know, grandkids and family to come and visit, and that's a great guest room that you could have for them.
Thank you.
Steve, jump in. We got about a minute left. I can't hear your audio, Steve. Can others hear him?
I'm not able to hear anything.
Oh, can you hear me now?
Yes.
Now we got you.
Okay, sorry about that. Did you guys do any lighting studies or simulations or anything to verify your daylighting?
We kind of basically I guess it was really preliminary, just making sure that our south facade had most of our windows on it. And we also tried to like have our open space concept so that daylight could go further, and just kind of like higher ceilings as well. So that was kind of, but I would say no, we didn't do like an actual study of how far that light would reach into the space.
Okay. And one last question, if I can, real quick, sorry. Did you guys take into account the possible addition of the elevators when you were doing your energy analysis too?
No, we did not.
Okay. Just something to think about.
Yeah, thank you.
Yeah.
All
And
right. I think we're out of time for questions. So thank you so much to University of Cincinnati. We enjoyed your presentation. And now we will welcome Toronto Metropolitan University to please pull up their slides.
Thank you.
When you're ready, you can get started.
Thank you very much. Okay, well, good morning. Today we're presenting Summerhill Place, which is located in Toronto, Ontario. Our team consists of myself, Adam Oliphant, Afrin, Ariel, and Sid Coghill, who is co-presenting with me today. We're one of the teams representing Toronto Metropolitan University, and we are partnered with a local sustainable building contractor.
Jumping right in, a key driver in the development of this project has been the ongoing housing shortage and related housing cost increases in Ontario, Canada. The province of Ontario has elected to address this through sacrificing high volumes of previously protected environmentally sensitive lands and restricting municipalities and conservation authorities' ability to refuse building permits due to heritage preservation and local green building standards in order to speed up development times. These sacrifices will not only result in further urban sprawl and environmental pollution, but are also in direct conflict with Canada's green building strategy for net zero emission building sector by 2050. Summerhill Place has been developed to demonstrate housing needs can be met without these sacrifices through providing sustainable, high-performance dwellings in already developed areas. In line with the identified drivers, project goals were established around responsible construction practices, democratic sustainability, and industry scalability through planful design, building performance optimization, and renewable energy in line with net zero energy and passive house standards.
To start, we selected an undesirable site in a desirable, low-density residential neighborhood in Toronto. The site is currently an underutilized parking lot surrounded by single and semi-detached homes and neighboring low-rise mixed-use buildings. The scheme we developed is a 3-story, 12-unit condominium. It totals 19,500 square foot of GFA and is comprised of 12 1,100 square foot interior footprint units. Toronto is listed as Zone 6 under the ASHRAE Climate Index, meaning it is primarily a heating climate with nearly 3,700 heating degree days and only around 400 cooling degree days. For the design, the remainder of our presentation follows the competition structure guidelines. We started by exploring potential massing of the site, first with the maximum allowable building volume per local bylaws. We then pulled in the sides and back of the mass to accommodate better lighting to the building and its neighbors. By subdividing the form, we established the stacks of units and circulation space, shown here in blue. Lastly, the roof was gently pitched and extended rearward to create a canopy above the rear balconies and accommodate a PV system. The outcome of which is a building that is scaled respectfully to the neighborhood, while natural wood finish on the cladding is aesthetically compatible with the surrounding urban fabric. This view also shows the shared access through the glass-walled buffer zone, a circulation space that provides both security and weather protection. Each unit has an identical layout, configured with either 2 bedrooms plus a den/office, or 3 bedrooms on the end units. Meanwhile, the circulation spaces are minimally conditioned to reduce the overall energy consumption.
Within the building enclosure, passive house quality assemblies were identified as a critical deliverable. These are provided through the highly insulated and airtight assemblies depicted here, separating the exterior environment from the interior for greater thermal control. Each unit and the buffer zone also maintain their own air barrier system to eliminate unwanted air movement between these spaces. Within the exterior wall assemblies, the primary air barrier is provided through taped and sealed plywood sheathing. A secondary air barrier system is provided by the high-performance Solatex Mento weather-resistant barrier. It is expected that these assemblies will achieve air tightness of 0.6 ACH. Insulation is provided in 2 layers, mineral wool batt within the stud cavity and dense pack insulation within the outboard Larson truss cavity. Advanced framing techniques have been used to reduce thermal bridging of framing elements. The highly insulated envelope achieves an effective R value of 50 when accounting for these framing elements. Vapor control is provided through a vapor control primer on the interior drywall, while exterior water is shed through a rain screen system. The project's active systems were selected based on their high efficiency to work within the energy budget provided by the PV array. A ground source heat pump system provides the space conditioning, while a hybrid electric heat pump is used for water heating. Energy usage is further reduced with an ERV, Energy Star rated appliances, and LED lighting systems. Water usage reductions are provided through WaterSense fixtures and supplemented by rainwater harvested and stored in cisterns on site. Living spaces within the city of Toronto are in high demand, with over 4K more needed each year until 2050. Those that are available are generally unaffordable for the average household. To own a dwelling in Toronto, the annual income required is currently 52% higher than the average households, while for 2023 renters, an equivalent apartment to those at Summerhill Place is 34% higher than the recommended average housing budget. In developing the preliminary costing model for Summerhill Place, the construction cost is estimated at $300 per square foot. Factoring in other expenses, its estimated units could be sold for $825,000, 35% below average price for a Toronto condo and close to an average household's budget. While Summerhill's utilities being 89% below average, the net savings over 30 years are estimated at over $580,000, making these units a better long-term financial decision. The combination of active and passive strategies used provide 55 to 75% energy savings when compared with more standard systems. The consistent ambient ground temperature utilized by the ground source heat pump and reduced heat losses through the enclosure, as well as the fairly consistent power provided by the solar array, add to the building's emergency preparedness, while the long lifespan of these systems reduce failure frequency. The combination of these equate to a durable and resilient project design. The project is a low embodied carbon due to its predominantly wood structural, mineral wool, loose fill, and dense packed cellulose insulations, as well as the natural wood products used in the siding, floors, and trims. From a preliminary evaluation, the project's embodied carbon is 50 to 60% lower than an Ontario equivalent. With zero operational carbon emissions, the project is 100% lower than an Ontario equivalent in this area.
Continuing from environmental impact, we endeavored to set an example by creating a highly replicable and democratic building. Geometric simplicity of the units allows them to be scaled and configured to suit many potential sites, though it is vertically limited to about 6 stories due to the wood construction. For the environment indoors, HVAC and lighting use integrated monitoring systems and autonomous scheduling. For example, each unit has entirely separate ventilation systems. In combination with CO2 sensing in the air, ERVs can run when needed to optimize energy use, fresh air, and thermal comfort. Additional consideration for air quality includes using low or no VOC interior finishes only and HEPA filters in fresh air supply systems. Sunlight entering each unit is controlled using exterior horizontal shading and occupant-controlled operable louvers. Additionally, a light shelf is used to diffuse light deeper into each unit. The resulting preliminary energy model generated using Energy Plus is estimated at 30,000 kilobTUs of energy annually, which represents, that's per unit, which represents a 40% reduction over an average Ontario low-rise condo unit. Additionally, the 116-panel PV array is estimated using helioscope to produce a net of 106.2 megawatt hours annually, meeting and potentially exceeding the total energy demand of the building. That concludes our presentation. Thank you for your time.
Thank you. We'll open it up for questions.
All right. Good job, guys. This was really good. Is there a plan at all for noise attenuation from that rail corridor that's right behind the building?
Yes, there is. Let me just scroll back up to, actually, I can show it on this plan here.
Okay.
We had included provisions for an earthen berm across the rear of the site, which we would then plant with coniferous shrubs and small trees, as well as wild vegetation. Additionally, I live quite close to this rail corridor, and it gets very infrequent traffic.
Yeah. But I get it. Okay. I'm not sure I have any other questions yet, so go ahead, Alex. Maybe he'll prime me for something else.
Yeah, Steve, I'm in the same camp. Very well done. We've covered the bases here. So could you go back and explain, I guess, would this be considered under the lines of affordable housing for the market? What's your targeted market again?
It's just to provide something that's more affordable than what's currently provided. It's not an affordable housing market. It's affordable for the average household income within Toronto. We're currently in a position here that, like, no one can buy a home if they didn't previously own a home. So we're just trying, again, like it's a 37% reduction over the average price for something equivalent in Toronto, and in line with what the average household income could afford.
Okay, and then with that reduction, and based on this proposed design, does it demonstrate to the city of Toronto meeting that goal of the housing that they want? Is there a targeted housing threshold they're trying to achieve?
Yeah, so they are trying to achieve 4,000 plus units each year until 2050. So there is a demand for a significant amount of housing within the city of Toronto, which is already a highly densified area. Toronto also employs its own green building standard, which pushes projects to be near passive standard anyways, which has created a little bit of jumble for some residential builders in the area, given it's not very conducive to incredibly high-rise towers and more typical buildings that are currently existing there. So we're looking to provide an example of something that's scalable and can fit on most sites, still available within the city of Toronto, and is a cost-effective solution to the housing shortage.
While also being a nice place to live.
Yes.
Right. No, absolutely. Now, with all that being said, were there any thoughts on to scaling it in a way that does meet affordable market rates? What does that look like to achieving that 4,000 units per year?
So for this site, we are at the height maximum for this site. If you could continue to go up to the 6 stories, that would significantly reduce the price, given it's the land that's the expensive component here more than the building components.
Okay, thank you. That's all that I have for now. Steve?
I'm good.
Excellent. Thank you so much, everybody.
Thank you.
Thank you.
All right, we'll give the jurors a few moments to take any notes they might have, and thank you so much to Toronto Metropolitan University. We welcome Penn State, or the Pennsylvania State University, to go ahead and pull up their slides, and we will begin at 11:50 a.m. Eastern Time.
Just to make sure, can everyone hear me okay?
Yes.
Yep, we got you. Am I good on mine end as well?
Yes.
Yes.
Okay, that's good. Thank you.
All right, if you guys are ready, you can go ahead and get started.
All right, thank you very much. Well, hello everyone. We are the Penn State Solar Decathlon team, and we're here to share our design of the Solar Chase townhomes. These townhomes are a reworking of a design that's currently used by one of the highest quality central PA production builders, SNA Homes. While these are considered high quality for the area, they are not high performance by Zero Energy Ready Home standards. Goals for this project pertaining to each stakeholder are shown here, and the Penn State student team shares each of these goals. These units are designed to be built near Pleasant Gap, Pennsylvania. This is in climate zone 5A and is heating dominated. As seen on the right, 10 units are under construction, while the site has room for 35 more, which are mostly south facing.
And so SNA currently owns several different properties around Pennsylvania, and the center is the Center County area, which is where Solar Chase is located. And so SNA currently owns several different properties shown in red that have very similar property portfolios, which consist of single families and townhomes. And this means Solar Chase townhomes can be easily replicable and mass produced, at least in these properties. And so we will focus on Pleasant Gap, shown in blue, as a case study, since this is where the existing Redfield townhomes are being built. Courtesy of Zillow, this graph shows how expensive State College housing prices have gotten compared to the Pleasant Gap, shown in green. And this is mainly due to State College being a large and dense college town. And this shows why Pleasant Gap has become one of the more popular places for new homeowners in the area, and why people are starting to live outside of the State College area. But even though the household income in the graph
shown on this graph is skewed towards the upper middle class. The median income is still around $67,000 US. And this means that Solar Chase townhomes cannot become too expensive for new potential home buyers, as it may deter them from buying these properties. And currently, Berks Home and SBA Homes are the only two production townhome builders in the area. And so we plan on having Solar Chase townhomes become a trendsetter for new townhomes for both of these companies and potentially the new ones as well.
So why redesign a proven product? Let's take a look at the average new construction on these lots versus the Solar Chase units. Although it is a slightly higher initial investment, the combined monthly cost of ownership is lower for a Solar Chase home as it achieves net zero performance. These units also provide the occupant with healthier air and greater comfort. Scalability is key and can be boosted once other builders are pushed to follow suit and make their own high-performance units. So far, our team has been educated about building science, collaborated with SNA Homes to establish goals and constraints, visited the existing site, developed design concepts, and presented them to Penn State faculty for feedback. Now let's take a look at some highlights of the architectural changes.
For the architecture team, we were interested in looking at the existing townhomes and seeing how we could make some changes to create more efficient living spaces, optimize circulation, and cluster plumbing. We wanted to keep the existing footprint of the building, but change the interior. On the first floor, we wanted to reconfigure the kitchen to allow for more solar gain throughout the space, as well as we moved the stairs down 2 feet to incorporate a mechanical chase. We also clustered plumbing in a wet wall on the left side of the plan. On the second floor, we wanted to optimize the use of the circulation in the main hall as it was a really tight corridor. So we decided to turn the second bathroom to cluster plumbing, as well as reconfigured the main space to have the linen closet where the existing washer dryer used to be. Throughout the project, we extended the roof overhang 2 feet to shade the south facade. For the existing siding, we saw that they used vinyl siding as well as stone veneer and asphalt roof tiles, and our main goal was to lower the embodied carbon by choosing new materials that were locally sourced. For our proposal, we currently have concrete roof tiles, respawn Shishugibon siding, as well as a different stone veneer, and we were able to find local manufacturers for all of these options.
By using a fly ash mix, concrete shingles, and wood siding, we were able to reduce the embodied carbon of our building. However, embodied carbon is something that we plan to explore more as we finish up this project. Next, we will explore some of the enclosure and mechanical design that allowed us to reduce the site EUI to 6.03 kilowatt hours per square foot per year. Before we do, we would like to share that these decisions were largely made based on cost optimization using VOPT and using FIAS recommendations for enclosures. Our first point of focus was air sealing, since SNA expressed to us that this would be one of their biggest challenges moving forward. In these pictures from the site, we can see holes and tears in the primary air barrier as well as tape peeling off of the seams. These are accounted for in our design by using zip R sheathing, which will be shown later. An SNA project manager shared that one of the leakiest areas in these units is the demising wall due to penetrations in the interior drywall. We chose to change their design from a single 2-hour firewall with dense glass to 2 1-hour firewalls, as this was recently allowed by a code change. The interior fire sheathing layers are taped and act as air barriers, so an unlimited number of penetrations can be made in the drywall without affecting the air barrier. A Pennsylvania Housing Research Center employee pointed out that another likely source of air leakage is the ceiling below the roof trusses. To solve this, our design has an air barrier stapled to the trusses and taped to the third floor top plate. 2x6s are then used to make space for utilities, and the gypsum is attached to the underside of the 2x6s. Next, we will explore thermal control. The insulation in the Solar Chase units exceeds 2021 IECC in all aspects and ensures durability of the envelope by mitigating condensation risk.
This main exterior wall assembly shows our updated wall with the zip R sheathing with integrated WRB, wearing for the rain screen and the new architectural siding. The corner detail on the left shows the exterior walls where the units are connected with our updated 2-inch palito and the OSB and the 2 1-hour rated firewalls. The corner detail on the right shows the new foundation insulation detail with our 48-inch rigid insulation in both the vertical and horizontal directions.
Our design partner also expressed their desire for updated mechanical systems in the new units. For this reason, our design includes a heat pump water heater and an ERV for energy recuperation, sized using indoor Air Plus standards. The units also feature a 2-ton ductless mini split system with an energy factor above 3 in most cases. And with these systems, the units are now 100% electric. Our design has at least one ERV supply and return, as well as a mini split head on each floor. We also prioritize clustering water fixtures to reduce the amount of water wasted when waiting for hot water. So now that we've shared some of the highlights of our design, let's take a look at the energy performance. As stated earlier, each unit has a site EUI of around 6 kilowatt hours per foot squared per year, which yields a HERS without PV of 33. With 7.5 kilowatts installed separately on each roof, we reach net zero status and a HERS of 0. As we finish up this project, our plan is to present this progress to our design partner for feedback, then conduct embodied carbon and plug load studies. Next, we will confirm our energy predictions using REM rate and perform an in-depth cost analysis using RS means and through conversations with suppliers and subcontractors. So as you can see, upon completion, Solar Chase will be a replicable net zero home that prioritizes high efficiency and occupant comfort for an appropriate price. Thank you.
With that, let's move on to questions and answers. I apologize, we're out of time.
I guess I'll go, Steve.
Go ahead.
All right. Yeah, great job, ladies and gentlemen. Great project. Let me ask, what's the complex real-world issues this project is addressing?
I would say that there are a lot of young professionals in State College who can afford a home on a double income of between $300,000 to $350,000. And there are a lot of options for townhomes on the market, but none of those take into account any kind of energy performance or embodied carbon in those buildings. And what we're trying to do is basically push the housing market forward so that the new standard for townhomes is something that is better for our environment and better for the occupants.
Okay, great. Appreciate that. Any thoughts as far as once the occupants, if the project determined once an occupant is in the space, how are we going to validate that they're meeting net zero while it's in use?
Right, it's a good question, because the 7.5 kilowatts to reach net zero is a very general case based on an energy model. There is enough room on the roof to put anywhere from 6.5 to 8.5 kilowatts. Obviously, we want to minimize that, but there is, with these ductless mini splits, there is a way for them to be programmable. So we think that would help make things a little bit more uniform. But that's a good point. That's definitely something that we should look into further as we finish this up.
All right, appreciate it. Thank you, Steve.
Thank you.
All right, thanks. Kind of building off the last presentation and what Alex just asked you, is there any thought being given by either you guys or the builder to making these houses more affordable for lower income families?
Yeah, definitely. That it would be great if this was more affordable for lower income families. And what we could kind of do when we finally present this to our design partner for the final would be kind of a tiered list. So maybe using Larson trusses instead of Zip R. We chose Zip R basically because it's a really builder friendly material. But yeah, we also feel like there is a sort of desire in our market around State College. You know, there's a market for sustainability. So that's sort of something that we considered as well. So yeah.
Yeah. Okay. And then kind of one more question related to that. Are the builders, based on what you were saying, with the builders and the air leakage issues and the things like that that they have, are they looking towards maybe panel construction, panelizing some of their designs to make that a little bit easier?
That's not something that we've really discussed with them, but we could definitely bring that up in the feedback meeting and see what they would think about it.
It might bring your construction costs down a little bit more too, towards that affordability range. And then again, if you're making those panels, it might be easier to make them airtight. And then you just have to worry about the connections. And I say that like the connections aren't a big deal, but you know.
Understood. Well, thank you very much.
Yeah. Good job though.
Thanks.
I do like it. That's it for me.
All right. Well, if there aren't any more questions, I would like to go ahead and thank Pennsylvania State University for presenting to us today. We really appreciated it. And in fact, we have appreciated all of your presentations so much. It's been so fascinating to see all of your hard work. I know this took a lot of effort, but it's been incredibly impressive to see what you guys have come up with. So thank you so much for sharing with us. We will now be, the jurors and ourselves will now be breaking to go through all of your presentations and come up with scores. If you would join the Zoom link for the Design Challenge finalist announcements at 2 p.m. Eastern Time. Please shoot me a message if you do not have a link for that. We can get it to you, but we hope to see you all there where we will be announcing the 10 universities that will be moving on to the next phase. And thank you again. Please enjoy the rest of the Solar Decathlon semifinal competition event, and we appreciate all of your hard work. So
Great job, all. Yeah, thanks so much.
Yeah. Thank you, everybody. Very impressive.